Hi everyone, welcome back to ChemHelp ASAP. In this video, we are going to be talking about half-life for first order reactions. Let's get started. So if we have a reaction A going to B, here is our differential rate law, sometimes just called the rate law. We've already specified that we're working with a first order reaction, which means our A here is just raised to the 1. That means our integrated rate law looks like this. But for a half-life, we can simplify this expression. All right, the first thing I'm going to do is rearrange the rate law so it looks more like this. Again, I want this ratio of A naught to A. Because of course, for a half-life, it means I have half of my reactant A left. So that means A over A naught equals 1/2. Or you can also think of this as A equals A naught over 2. Again, these are just the same expression, simply rearranged. I'm going to take this expression for A and I'm going to plug it into my denominator right here. That gives me this expression right here. You'll notice that I've made my T now T 1/2 because that is my half-life. And this is why I chose this ratio, because what does this ratio simplify to at this point? It just simplifies to the natural log of 2. This is actually a number. You can calculate the natural log of 2. Of course, our kt 1/2 stays the same. So let's say I'm going to solve for t 1/2. I get this expression right here. Again, where this 0.693 is simply the value of natural log of 2. So sometimes you will see this expression written not with the 0.693, but with natural log of 2 in the numerator. It's both the same thing. Let's use this equation in an example. Okay, so we have, again, a first order reaction that's really important because this half-life is specifically for a first order reaction. It has a half-life of 20 seconds. We want to calculate K, and then we want to know how much time is required for the reaction to be 75% complete. Okay, let's take this one step at a time. We first need to calculate K. Okay, here is our expression for half-life. We know what our half-life is. The problem gives us that. That's 20 seconds. So plugging in our 20 seconds here, we're just simply solving for K. And K is 3.47 times 10 to the negative second. And that, of course, is per seconds. Okay, so next we want to know how much time is required for the reaction to be 75% complete. So to make things simpler, I'm just going to assume that my A naught is 100 molar and my concentration of A is 25 molar. That is 75% complete. What this assumption helps me do is figure out this ratio of A naught to A. That is just going to be 100 molar over 25 molar, which is 4. Having something be 75% complete, you could probably get to this 4 without having to do quite this much work. But if you've got a situation where you're looking for a reaction and it's going to be 82.5% complete, then it's nice to know how to set this up so you get this correct number right here. Okay, since I know this ratio, I'm going to be plugging into this form of my equation. So simply plugging in, I've got the natural log of 4. I've already found my value of K. It's right here. I'm solving for T, and my time is 40 seconds. This makes sense because if the reaction is going to be 75% complete, I'm going to go through 2 of my half-lives. I hope you found this video helpful, and thanks so much for watching.